So yeah, so what's the purpose of factor analysis, both exploratory and confirmatory for that matter? Well, I guess you can see it in two different ways. One is that one of the aims of psychology is often to measure latent things. Intelligence, it's not a thing you can see. It manifests in behavior, and we infer its existence from behavior. So in a typical way, we'd infer the existence of intelligence from a set of responses to an intelligence test. Or we might infer the existence of conscientiousness, which we can't actually see directly, but we can observe through ratings on a whole bunch of items that meant to reflect conscientiousness. So yeah, it's definitely a tool for trying to extract those latent factors, to estimate what they are. It's particularly useful where you have a multifactorial test. Like a measure of the Big Five personality or any personality measure, it's meant to be measuring different constructs, extroversion, conscientiousness, and so on. Or maybe you have a climate survey and it's measuring satisfaction with management, satisfaction with pay and benefits, satisfaction with promotional opportunities, and you're wanting to see whether these discrete dimensions are emerging in the data. So it's certainly a tool for verifying, particularly multi-factor tests, that the items are grouping in the ways that you expect, and it's a way of extracting those scores. It can also be used simply as a data reduction tool. If you have a lot of variables and you just want to simplify it, you've just measured a whole pile of things and you're trying to reduce it down, then principal components or factor analysis can guide you in that process of working out, what are the underlying dimensions of this data set. That's certainly an important approach and can be used to sort of reduce the number of predictors for a regression equation or just understand a set of variables. So in terms of applications, you might be given a test and you want to check that it's behaving as it should be. There are 5 factors in this Big Five test. Or maybe you're refining or wanting to reduce the number of items in a test. You can work out which items to get rid of. It's also used for data reduction. And in particular, this is often like a first thing. If you're presenting a thesis, you check your scales, reliability, and factor analyses. And then you say, okay, they're good. I'll score my tests and then run some regressions or correlations. And probably any of you have done like survey type theses in the past. That's probably what you did. Yeah. So in terms of, there are lots of ways of breaking up the kind of assumptions or requirements for factor analysis. We talk about factorability, sample size, linear relationships, and variables on the right metric. So in terms of factorability, one way of thinking about it is just that things are correlated. There's no point talking about latent factors if all your variables are uncorrelated. If the items don't share anything, then there's going to be no dimensions underlying those variables. So the first assumption is that there is some degree of correlation between your variables. And so, for example, in a personality test, you're assuming that other extroversion items are correlating with other extroversion items, and conscientiousness items correlate with other conscientiousness items. This measure of sampling adequacy is an overall metric that sort of looks at the pattern of correlations and extracts out an overall index of suitability for factor analysis. And SPSS does provide this. In terms of sample size, there are a lot of rules of thumb out there. Bigger sample sizes are better. You're going to get a more accurate picture of the true relationships between items and factors. There are things that affect how important sample size is. The clearer the factor structure, the higher the correlations between items, the less you'll need big samples. And in general, the more items, probably, and the fewer items per factor, you probably need bigger sample sizes. If you're just looking for like a little rule of thumb to get started, I usually go with the idea of 200, I can probably start doing factor analyses. Maybe 100, I could probably still do it, but I'd treat it with a bit of caution. And it probably does depend a little bit on your application. So if you're just trying to check a scale and to look like, oh, is it performing about right? You know, a couple of hundred would be fine. If you're really wanting to publish a paper where you're refining a test, then you might want more. And sometimes even you'd have two samples, like one where you refine, drop items, check things, do all that stuff, and then you check in a separate sample just how well that looks, just in case you're picking up on chance when you're refining the test. But, you know, so often, you know, for typical survey type studies in psychology where you might have a few hundred people doing it, then factor analysis is usually pretty robust. One bit of information that can be useful when understanding whether an item is captured by a factor model and whether it should be sort of retained or whether you maybe even need more factors is the communality. This tells you the proportion of variance in the item that is captured by the extracted factors. So if an item is a large proportion is explained by the extracted factors, it means that it's represented by the factor structure. If you get a very low communality, it implies either that it could mean that it's just sort of a rogue item and you don't want it. It's just measuring nothing much at all. Alternatively, it could mean that it's a factor, but you just didn't measure other items on that factor. So actually, it's reflecting something that you should be measuring, adding more items. You know, it's a particular construct you haven't tapped into with other items, and it's not really there. So that may indicate maybe you want to get a few more items on that construct. It's usually a bit of a judgment call. It might also imply that if items have very large means or very small means, you're getting floor or ceiling effects, they should be discarded. So in general, you can look at the communality to flag items that should be removed.
When it says rough rules of thumb, is that a particular test that we performed?
Nah,
that, or?
That's just a heuristic.
Yeah.
And a lot of it does depend on the context. And often it's about comparing. You can look at all the items and you'll see that one or two items are much lower than the others. And often I would usually look at it in that kind of way. In some settings, I barely look at this at all because it's like a personality test. They're all going to be kind of reasonable usually, but sort of often depends. If it's an established scale, then most of them will generally be okay anyway. Other times, if you're refining your own scale and you're more keen to throw out low-performing items or strange items, then you'll be looking at this more carefully. So, yeah, the other big question that there's 1,000,001 opinions about is how many factors to extract. I don't know if anyone's ever had to refine a scale or a test or anything like that and been confronted with this issue about how many factors you should pull out. But yeah, it's definitely, there are 1,000,001 rules out there. A lot of people confuse the fact, you know, they go into SPSS and they run their factor analysis and they say, oh, I've got 5 factors or I've got 6 factors. And it's always important to remember that what you did was you let SPSS apply a rule, which is eigenvalues over 1, and it selected a number of factors. So you could say that you don't have a certain number of factors, rather you implicitly chose to use the default rule in SPSS, which is eigenvalues over 1, and that the application of that rule led to a certain number of factors. So that distinction is important because the eigenvalues over 1 rule is generally pretty bad, or not a great rule of thumb. Yeah, so
that's not great.
Not a good rule, no, in my opinion. It'll generally extract too many factors, or at the very least, often it will pull out like borderline factors. You know, like often say if you've got a measure of the big 5, there will be 5 main factors. And then you can sort of see that there is something systematic going on at the 6th and 7th factor. But it's almost noise. It's maybe like a little bit more than noise. Who knows what it exactly is. So, yeah.
Is this with the eigenvalues over 1?
Yeah. The eigenvalues over 1 will generally extract probably too many on most tests. Like you hear people looking at a big 5 measure, and the eigenvalues over 1 will tell them, oh, there's 18 factors or something like that. You know, way too many. In my opinion, yeah, better tests. The parallel test's quite nice. There is syntax files floating around that will implement that for SPSS. It simulates random data and looks at how many, like the distribution of eigenvalues for simulated data, and sort of looks to see whether your data has which factors have higher eigenvalues than the random data, and if it's however many that is, that's the recommended factors. Another approach is to look at the Scree plot. That's probably my preferred way. It takes a bit of practice to read a Scree plot, but we'll look at an example in a bit. I'll show you in a bit, but that's quite a nice approach. I wouldn't neglect theory. If you have an established test, you know it's 5 factors, or that's how it's always scored, or you know it's 3 factors, it's always scored that way. Often you're just wanting to check, is the test performing right? Does that look reasonable? There might be a little bit of systematic variance beyond those factors, but it should get you most of the way. So certainly theory is a good guiding principle, and there are a bunch of others. So what I would usually do is look at the Scree plot to see what that's suggesting, think about theory, think about my purpose of my analysis, maybe have a look at extracting 1 or 2 more or 1 or 2 less factors, and often looking at the factor loading matrix and seeing whether, if you're not getting any straggling factors or it doesn't look like you're collapsing factors, you might get it about right. So there's quite a bit of art in all this. The Scree plot I think is really informative. When you run factor analysis or principal components analysis, the idea is that it finds a latent vector that explains the most variances possible. And then it looks for a second factor that explains the next most amount of variance that's different to what the first factor did, and so on and so on. And so you end up getting these kind of patterns. So these are the extracted components, and this is the eigenvalue. Well, in some sense, the variance explained by that factor. So what we see here is that the first factor explained a lot. The second one explained about 1/3 of the first one. So the big one's doing, this first one's doing a lot of the story. And then we've got a reasonable one there. And that's, the third one's not much less than the second. You've got a fourth one that's another about half again. And then you've got what's called the Scree. I guess it's a mountaineering term of the rubble at the bottom of the cliff. You don't want the rubble at the bottom of the cliff. So you find the start of where the rubble begins, where it sort of just looks like a steady slope of randomness, and you go up one. So this is saying there's 1, 2, 3, 4 systematic factors. So yeah, that's not a bad rule. Occasionally it's a little less clear and you can get like a slight difference down here where it's a bit borderline, but yeah, that's probably not a bad approach to justifying a number of factors. And it's even just quite informative to note that, oh yeah, the first factor is really the biggest thing, and then these other ones are much smaller, or is it more even of a clearly sort of initial set of factors and then the Scree, so on. Yeah.
With the eigenvalues that are lower, say for 2, 3, and 4, does that mean that they're not as strong a factor?
Yeah. Yeah, so if you were looking at we'll talk about rotations in a bit, but if you look at the unrotated solution, that first factor is going to express the most important chunk of variance. So if this looks a bit like maybe an intelligence test, where you've got a general ability factor, and then maybe there's like subcomponents that expect, like there's tests on verbal and psychomotor and perceptual or something like that. Or if this was, I've seen this in climate surveys. And they've got 1 million different scales in a climate survey. Satisfaction with boss, satisfaction with pay, and so on. But the first factor's up here. And that's, are you satisfied? And then you've got all these little tiny weeny factors like, well, relative to your satisfaction, how your boss or this or that. But so that can be quite interesting that, okay, you can get 95% of the story by just understanding, well, is this person happy or not?
Yeah.
And then there's these little things that are like, well, in particular, are you satisfied with your boss or your stuff like that? So it can be quite informative to look at that profile and say, do you have a big first factor and that's everything? Or is it like, no, there's several kind of meaningful ones and then it drops off? Yeah.
And is that based on the inter-item correlations, strength of the level of the eigenvalue, the number?
Yeah, I guess so. I mean, under the hood, it's based on the correlations between the items, yeah.
Is that how it pulls out the factors, the strength of how they correlate, the items correlate that load on that factor?
Yeah, it's based on the pattern of correlations. And so I guess if every item intercorrelated highly, then you would expect to be more likely to see like a global factor. I guess I'm not going into the matrix algebra under the hood here, but that would be the theme, that if, you're more likely to have a global factor if everything's intercorrelated highly. Whereas if you have pockets of correlations, so all the conscientiousness items intercorrelate, but they don't correlate with anything else, and all the emotional stability correlate, but don't correlate with anything else, you're likely to see discrete factors here because underlying variables are going to only explain one of those clusters of
Yeah,
variables.
I was just wondering how it pulled them out.
Yeah, so it's definitely based on the correlations between the
Jeremy,
items.
what were you meaning in the context of like the 5-factor personality test? If one of them was up here and the rest were there?
Yeah, so good you asked. No, I'm doing a bit of research actually on that issue at the moment. There's quite a bit of discussion about what they call the big one. So the theory goes big 5 is orthogonal, so each factor is uncorrelated. But actually in a lot of studies they find correlations. So kind of the good poles, if you could say so, the conscientiousness correlates with emotional stability, correlates with extroversion, a little bit. You see correlations and you do see a bit of a big one. And the general school of thought says, well, maybe this thing's measuring social desirability. And then the interesting theoretical question is this real? That some people are just more socially adjusted? Or is it a response bias thing? That it's just that some people either deceive themselves about their social desirability or are lying on a test to different amounts.
So it's not like one big personality factor, like you have more personality than I do.
Well, yeah, more socially desirable, I guess. Well, if there is a global factor that comes out, it's like, well, it means you're a bit higher on all the big 5, where neuroticism is flipped to emotional stability. So that, I think that's a really interesting question about what that means. But and some tests you see it more than others, and in particular in selection settings you see a bit more of it, perhaps with the assumption that people are faking to different degrees, and that faking is driving a bit of the observed correlations. So, but yeah, in personality testing, you'd hope to see more, and we'll see what we get later on, but you should see more like 1, 2, 3, 4, 5. Yeah. I think I've said that. That's what the factor analytic procedure does initially. Extracts, latent variables that it can explain the most variance in the data for a first factor, and then finds an uncorrelated second latent factor that predicts as much of the observed items that's distinct from the first, and so on. So the result is for each component or factor that you extract, you get different metrics for describing the variance explained by those factors. You can either get percentage of total variance explained, or eigenvalues is another metric where the unit of 1 represents the variance of one item. So if you had 50 items, first factor has an eigenvalue of 10, it's kind of explaining 10 over 50, so that's 20% of variance. When we run these factor analyses, so each factor has a certain amount of variance, and I guess more important ones come first. We can look at how each item loads on those factors. So in order to interpret those factors, we need to say, well, what does it mean to be high on the factor? Which items are more important? And so we extract these factor loadings, and we can also rotate them to increase the interpretability. Let's go to that now. So 2 seconds, I'll get to that one. So once you've decided how many factors you've got, you then have the task of interpreting these components, these factors. So you want to give a name to it. So if you didn't know that all these items, like I work hard, I follow orders, I am dutiful, I keep my office clean. If you didn't know what that factor was going to be, you'd have to go to the items and, oh yeah, you see that those items load on this factor, and you go, what's common about these items? Oh, it's sort of a conscientiousness thing. So the first aim is really to look at how much each item loads on a given factor, what it means to be high, and trying to give a name to that commonality. So we can either look at the unrotated or the rotated solution. So I'll explain rotation in a second, but the unrotated solution means that the first component is the most important one, and then your second and third is progressively less important. So it's not always clean. It doesn't always follow what they call simple structure. Rather, every item might load on the first factor because they're all job satisfaction items in one way or another. Or every ability test loads on the first factor because they all kind of tap in some way to cognitive ability. Whereas, in contrast, a rotation will kind of redistribute the variance across the factors and try and ensure a one-to-one mapping between variables and factors. And so once you do that, you often see that, the 3 verbal ability tests load on one factor and the 3 spatial load on another. Or the 5 manager satisfaction items are loading on one factor and the 7 pay and benefit items are loading on another. So it can rotation often makes interpretation a little cleaner. We'll go through a couple of examples in a bit. In general, when it comes to rotation, you have a choice between orthogonal, i.e. uncorrelated rotation, and oblique, which allows for correlated rotation. There's a bunch of different ones that use slightly different rules about what they're trying to optimize. Certainly Varimax is a very common one that you'll see in the literature. I quite like Promax. I quite like correlated factors just because it seems to make intuitive sense that often in psychology we have latent factors, but they do tend to be correlated. So it makes sense to me that if I was measuring different cognitive ability measures, that they would be distinct but correlated. So I quite like the clarity of Promax rotation.
What might make you choose a direct Oblique instead of Promax? Is there a big difference between them?
I don't think so. To be honest, I'm not sure. I mean, there is whole literatures you can read about, what difference does it make and what are the pros and cons. I think there's a difference between oblique and orthogonal that's fairly decent because it's saying like, well, we're going to let these factors correlate or not. You can always train your intuition by trying it different ways, and generally you'll find it doesn't make much difference really. You want to be a little bit careful about like what rules you use. Like, it makes me look good is obviously not the ideal rule versus, it's just a principled approach. But to be honest, a lot of these things, there's 5 different approaches and it doesn't make much difference. So, it's very easy, I think, just get bogged down in like all these little choices. I just tend to use Promax every time, and I think a lot of people would have their little rules that they just use every time, and probably doesn't make too much difference. You can play around with it and see it if you want. I don't think the literature's that clear on what is better anyway. and what does better mean in this context. It's just a means of clarifying the structure. In some ways, any of these are legitimate representations of the factors. Yeah. And most of the time, you'll find that the items that are loading together with one are the same with another. But as I say, play around and see if you're kind of wanting to train your intuition. Yeah. I mean, under the hood, it's based on matrix algebra, but the traditional way of thinking about it was, and I think this is what they actually did and why they call it rotation originally. I don't think it's quite the same with all the matrix algebra and stuff, but the idea is that, say you had two factors. Imagine you've got two factors, an x plane and a y plane, and you've got items, and they're loading on both factors. So they're up in this quadrant. What if we rotated the axes? Now these items are actually high on this factor and 0 on the other factor. So that was the traditional metaphor, and actually how they did it is they rotated the plane. So it's not really changing the position of the items, but kind of rotating the plane to put them so that they're more clearly on one dimension. So. Well, the initial extracting is trying to maximize the loadings on the first factor, and then on the second, and then on the third. So this then reallocates that in such a way to define those, sort of redistribute the variance across the factors, and in so doing it.
Find the best fit across all of them, like it keeps on going, but just find.
Yeah, it's using I guess it's trying different permutations to try and get what they call simple structure. And I think that's basically how the different algorithms differ in what they define as simple structure. But the logic is that each item should load on one and only one factor. So you've got, So that's what, I think essentially what the algorithms differ is trying to achieve that goal. If you really can, you can look at the sort of, it's all matrix algebra, multiplying matrices and so on to try and redistribute variance. So books like Tabachnik and Fidel might be, if you're really curious to get a bit more of that deeper understanding. There you go. Is that all right? Okay. But let's look at an example, and this, it's all right to talk about an abstract, but let's look at an actual example. This was from some very old thesis data of mine. It was motivated by predicting performance, but we measured people on 9 ability tests, and it was based on the theory by Philip Ackerman, which said that cognitive ability was important when people first start learning a task, and perceptual speed is important in the middle, and psychomotor speed was important at the end. So, we were testing this theory. So we had 3 what were broadly labelled as cognitive tests. So one was looking at cubes and seeing whether they were the same or different. One was a kind of a logical reasoning task, ask you to work out what's a logical inference from a given scenario. It was an advanced vocabulary test, so asking you about what an obscure word means. So they were our cognitive tests. We then had 3 perceptual speed tests. One was, a clerical speed test. You looked at some letters and numbers, and you had to find the matching one in a set, and you had to do it really quickly. And your score was how many you correctly did in a minute. There was the number sort. So that was find the smallest, or in some cases the largest number in a set. You see how quickly you can do that. Number comparison, I think, was just, are these 2 numbers the same or different? And they were like long strings of digits. So they were the perceptual speed tests. And then finally there were 3 what we called psychomotor tests. There was a simple reaction time, flash of a light, how quickly can you press a button? 2 choice, press the right button as quickly as possible. Or 4 choice, 4 lights, pick the right one. So yeah, we've got the proportion correct for the different tests, or number completed in a minute, or milliseconds reaction time. So obviously it gets slower. Okay, so I looked at the communalities and also theory. Theory said 3 factors, and when we looked at the communalities using principal components analysis, we can see the percentage of variance that test shares with the extracted 3 components. Okay, so what do we see? They're mostly pretty large, so mostly 70, 80%. We had this one test, the cube comparison, which was a bit of a nuisance. So it clearly was not as well represented by 3 factors than the other tests. And perhaps as we go forward, there'll be a story about why that is. Perhaps there was something a bit different about that test, or it wasn't very good. If we want to verify that how many factors, I said 3 is what theory says. General ability, perceptual speed, psychomotor. But what does the Scree plot say? So we've clearly got our G factor here, or a general kind of ability. There's a pretty clear second. And this is more of a classic example where it gets a bit fuzzy. I would interpret this to say the third and the fourth do stand out from the Scree, but it's not super clear and it's a little fuzzy. So, and perhaps that's reflecting the fact that we don't have a lot of tests per factor, and we have this odd cube comparison that might sort of be its own factor in itself or something like that. So there's kind of 3 main factors, but maybe with a bit of noise. You notice in this case, eigenvalues over 1 is giving us 3. And I'd say that's probably about typical for a test like this where you've only got 3 items per factor. Where it starts going a bit crazy is when you've got like 10 items per factor, like on personality tests. Then you often get lots of extra ones. Okay. So when we extracted 3 factors, we see that the first factor explained 42% of variance. That's our G factor, I guess. And then we'll have to look to see what these other factors are, but they had another 18, another 12%. Yeah, and when we applied a rotation, those first 2 factors were more evenly weighted. Okay.
So what did you say to that when you applied this?
So we applied a rotation, and so we can see that the eigenvalue, so an eigenvalue of 3 in this context, there's 9 tests, so it's out of 9. So 3 items is a third, I guess. I think because I used a correlated rotation. These numbers can actually add up to more than the unrotated numbers, if that makes sense. Because so when you've got rotated factors, the sum of the variance explained by each factor can be more than the individual ones because they're overlapping, so they're sharing variance explained. But the point is here that you can get a sense of how big they are. So it's about a third of all the variance, and this is about 2/3. So the first 2 rotated were slightly more important than the third. But probably the big issue now is what do the factors mean? So can we have? No. So here's an example of an unrotated solution. So we don't have simple structure here. So remember here, the first factor in the unrotated solution is the most important. That's your G factor, I guess. And what we're seeing is that high scores mean high on this test, high on this test, well, high on all these tests and low on these. And given these are reaction time, longer reaction times mean less ability. So that makes sense that they're negative. We can also not only look at the direction of these numbers, but also the size of them. They're basically like correlations between the item and the factor. So these psychomotors are loading high, all these are loading high. Pretty much everything's loading high except for vocab and maybe cube comparison. So maybe there's something special about vocab that's quite distinct from what's common amongst these other measures. If we go to the second factor, it seems to be mostly inference and vocab. And interestingly, it's kind of loading positively on the psychomotor. So the slower people. My interpretation was that we have, and I noticed this, that some of the older, less computer savvy participants often had, they had very large vocabularies, they had a long history of reading, but they weren't necessarily the quickest. They hadn't maybe played as many computer games or whatever it might be. So there was sort of this kind of verbal, but not so quick on the psychomotor tests factor. And then we could go to the third and see what's left. The important point is that interpretation of an unrotated solution is a bit different. It's not like this clean, simple structure. Items are loading on multiple components, and it's a very different perspective on a test. In contrast, after applying a Promax rotation, everything gets much clearer. This factor it's all about the psychomotor. You can pretty much ignore these like below 0.2, 0.3 kind of loadings. But here we've clearly got, this is clearly technically it's a poor psychomotor performance. Longer, higher scores mean poorer, slower. The second factor is quite clear. It's very clearly the perceptual speed factor with maybe a little bit of cube comparison. And the third factor is clearly your general cognitive. Probably one of the themes of that is it's reiterating, look, the cube comparison test does not fit with this three-factor structure very well. And if anything, it's actually sharing a bit with the perceptual speed. So that might be a reason to kind of throw out the cube comparison test, or at least if you can, and think about. And when I reflected on that, the cube comparison test actually did have quite a lot of perceptual and speeded characteristics. So we've got an interpretation of our three factors, and we can verify that they group together or not from that factor loading table. And you can see how a rotated solution is quite different to the unrotated. Because we used a Promax rotation, we also get the correlations between the factors. So we can see that perceptual speed correlated, interestingly, where are we? Factor 1 is poor psychomotor performance, correlated negatively with perceptual speed, which makes sense that fast reaction time, fast at scanning numbers. And there was a little bit of a correlation between the perceptual speed and the cognitive. So you're good at one test, you're good at another, but probably not much of a correlation between the psychomotor and the cognitive.